So, how's my presentation so far? All right, well, I'm Walter Bright, and this is my favorite topic. Okay, I'm a very opinionated person. My experience is in compilers and languages is very narrow but very deep. And that's because I don't feel I actually understand a language until I've developed a compiler with it, until I've developed a compiler for it. So that kind of restricts the number of languages I'm very familiar with. A lot of these ideas you'll agree with. There's a lot you don't. You are not going to agree with. Some are obvious, some are not so obvious. Let's take a real simple case of implicit declaration of variables. Have any of you encountered that in a language? Come on, nobody uses Python? Okay, implicit declaration of variables pops up in new languages now and then, and they sound like a great idea. Why bother declaring a variable? Just the first time you use it, just automatically declare it. And it sounds like a great idea, and it's only after you use it for a while you realize that it just doesn't work. And the reason it doesn't work is it doesn't detect typos in your variable names. It just declares a new variable. And sometimes, like if you read your own text you write, you don't see the mistakes you make, and you keep reading that misspelling of your own variable name, and you don't recognize it, and it becomes a really hard to find bug. So a lot of these languages wind up enabling some way to try to back out of implicit declaration of variables. And the right thing to replace it with is a spell checker. And spell checkers, which use as their dictionary the symbols or the symbol table, turns out to be a very effective tool, and users like it a lot, and it's become very successful. Of course, some of these things I'm going to talk about, you're going to argue with. People argue with me about it all the time, and of course, if you're developing a programming language, you can do as you please, but don't say I didn't tell you. If you get anything out of this presentation, I'd like it if it would be a success if you kind of thought about programming languages from maybe a different perspective than you did before. Okay, the first thing is making your lexer independent of the rest of your compiler, and the parser independent of the rest of your compiler. Now, does anybody want to shout out the name of a language that doesn't follow this rule? No, just shout it out. C++ and its precursor C are infamous for requiring a symbol table to parse it. And it's kind of frustrating because it isn't even necessary with some simple changes to the language that can't be done because of backwards compatibility. This problem could be eliminated. So it's best to start up front and design it so that these are independent. There are downsides to doing this. For example, people often want to define their own operator tokens. Well, that means you need a symbol table. That means your lexer cannot be independent of the rest of the compiler. And so you do have to give things up to get a context-free grammar. Okay, if they are independent and standalone, they can be made pure. And pure has a lot of fun properties, mainly like resistance to bugs, a clear definition of what goes in and goes out, no dependence on global variables. It also means that it becomes then easy to build a syntax highlighter. And the reason you want it to be easy to build a syntax highlighter is you want to make it easy for people to write tools for your language. And the less trouble there is in writing the tools, the more likely they're going to write tools for your language, support your language, and you'll have a much bigger ecosystem out there. You can't write everything yourself. And a couple of examples are like a style checker or a reformatter, or the built-in support into an IDE for your language. Another important things, one of my controversial opinions is every compiler switch is a bug. And the reason it's a bug is it divides your language into two. Now you have two languages. For example, C compilers often have a switch as to whether chars are signed or unsigned. Isn't this terrible? Because now you have two languages. You have a C language where your chars are signed, and you have a C language where your chars are unsigned. And what happens when you compile one part of your program with one set of switches and another part of your program with a different setting for those switches? Are they compatible or not? Will they work together, or will bizarre things happen? Compiler switches are often a symptom of when the compiler or the language designer couldn't make up his mind about how the language should behave. So he tries to have it both ways. And when you're arguing with people, or hopefully simply debating, not arguing, about how a feature should work, sometimes somebody always proposes a compromise that says, why don't we put in a switch so that we don't have to make a decision? Well, you're going to be sorry you put in that switch. At some point, you have to stand up and say, this is the way we're going to do it. The same goes with a warning. If your language has warnings, every warning is a bug, is a failure of your language design because you didn't make up your mind how the semantics are supposed to work. So a lot of compilers have all kinds of different warning switches. And you'll find out that different compilers for the same language have different detect different warnings, and what happens is your language has split into an untold number of other languages that are all slightly incompatible with each other. So if you find yourself wanting to compromise and put a warning in, just realize that you're going to cause yourself a lot of trouble in the future. One thing I've discovered is, although this should seem pretty obvious, I'm a slow learner, better error messages are always better. The more context you can give to the user, the more suggestions on how to fix it to the user are all very much appreciated by your users and almost always a big win. Another important thing to consider is compatibility with existing code. Of course, the more you can be compatible with existing code, the larger your user base will be, because they can start integrating it into their existing projects. An example of that with the D programming language, a recent example, is I wound up building a C compiler into the D compiler to improve interoperability of the D language with C language. It's kind of a drastic step to build two compilers into one, but since I'd built a C compiler before, I knew how to do it, and it wasn't that much work to add it in. Okay, the C ABI. Your language may have nothing to do with C, but you'd better follow the C ABI. And I know this from bitter experience because I designed a better function ABI. And it turns out that there are a whole universe of tools that work with the binaries of your code, and they will not recognize your code if you don't follow the C ABI. Even worse are the symbolic debuggers supposedly follow the dwarf symbolic debug format, and you'll find out that this is false. What they follow is whatever the GCC compiler puts out, which may only bear a passing resemblance to what the specification for the dwarf symbolic debug info actually is. So the debugger is all grown up around following the C ABI of what GCC does. And if your compiler generates object code that is even slightly different, all your users will complain that the debuggers don't work with it, and the other binary code analyzers don't work with it. And even worse is a lot of program scanners will decide that any program built with your compiler is malware. And so customers will write a program using your compiler, and then they'll get the complaint that their customers are complaining that everything generated by the compiler is malware. And it isn't malware, it's just that they do not recognize the function calls and thinks there's some hanky-panky going on here. So I tried the good fight of doing something different, a better ABI. It just doesn't work. Save yourself the trouble. Here's an interesting thing. Documentation generators and unit test frameworks are usually separate programs. And what I've discovered was that if let's say the documentation generator is a separate program, is your program doesn't have any documentation. Who's experienced that? All these functions, no documentation, because it requires a third-party tool. And a third-party tool is never installed. It's the wrong version. Users do not want to read the manual for a third-party tool. I've seen these manuals for third-party tools sitting there shrink-wrapped on their shelf over their desk for years. They never broke it open. But when you build a documentation generator into the language, something magical happens is they start using it. And you can even write automated tools to say, no, you forgot to add the documentation to this function, and it doesn't follow the standard format and stuff like that. And my personal experience is this is transformative to your code and to your presentation and to your documentation. It's like a night and day difference between having it and not having it. Another problem with not building in a documentation generator is there's not one third-party tool to do it. There's an endless number of them, all different. So what happens when you have two different teams in your company and they each pick a different documentation generator, and now they can't be merged, or they can't work together? And then you'll have a big fight between the teams of who's going to win. And what a waste of time. If you build in the documentation, it may not be the best. Deoxygen is a better documentation generator. It doesn't matter. It's there. It's always there. It's always up to date. It's always in sync with the compiler that you're using, or the version. And it's going to work with your different teams who are using it. The same thing happens with unit tests. It completely transformed deprogramming when unit tests were built in to the language. And yes, the unit test is kind of primitive in D, but the difference between not having unit tests and having primitive unit tests is very dramatic and very transformative. By building it in, you sort of browbeat people into using it. And that works pretty good. When you're designing a language, you have one big decision to make. Do I use automatic memory management or not? And the two camps, as far as I can tell, are evenly divided. And the people who can use both seems to be a very small percentage of programmers. So I don't really have any good advice on that, because you simply can't please everyone with that. But one thing's for sure, manual memory management always takes longer. I don't mean longer in runtime, I mean developer time, because it's going to occupy a great deal of your developers' times or your users' time if you require some form of manual memory management. Another thing I learned the hard way is multi-threading is hard and almost nobody understands it. It's I remember the meetings with top C++ developers when they were trying to figure out how to do multi-threading in C++, and it was very clear that only about 3 people in the room actually understood what was going on. And the rest of us just it's really hard to figure out. So if in your design of a programming language, anything that will move towards making multi-threaded code work is going to be popular and much appreciated. The Go language, for example, has been very successful in using Go routines. Another big innovation, I think, as C# was the first to do it, is async await, is a big advance to making user-friendly, reliable, multi-threaded programming. So don't leave that up to chance. You have to have multi-threaded programming in a modern programming language and anything to make it easier. Another thing I see now and then is having multiple pointer types in a program. And this started back in the DOS days when you had near pointers and far pointers and huge pointers and code segment pointers and stack segment pointers and even a few other kinds of pointers in the menagerie. And you had to do it because DOS was such a peculiar machine. But if you don't have to do it, don't do it. More modern versions of this show up as having a different pointer type for a garbage collector pointer as opposed to a manually memory managed pointer. And the trouble with that is it all sounds great, but you wind up with 2 standard libraries, or 2 versions of every function, one with this kind of pointer and one with that kind of pointer. And it's not just that they're different pointer types, they require different implementations of the library functions. So this really jumps up to cause all kinds of problems. And I suggest it just isn't worth it. You will be sorry if you don't settle on a single pointer type. One thing modern people or programmers do, well, programmers have always done, is the code has to be portable. So the more fundamentally portable your language semantics are, the more your users will love you for it. The idea is I can develop on one machine, compile it on another machine, and it works right out of the box, no problems. A couple things to move in that direction is the size of an integer should be fixed. So it's the same on every platform, regardless of the machine. And fortunately, modern CPUs have sort of converged on the idea that ints are 32 bits. Even on 64-bit machines, ints are still 32 bits. Over the years, I've seen enormous effort by people working with C, trying to make their code portable, and trying to figure out what to do when C doesn't set the size of an integer. And almost always, the code is that they do in good faith, and they try very hard, is it's simply wrong because they've never ported code to different platforms before, and it's just kind of sad. I've seen that effort over and over and over again, and program after program tries to abstract away the size of an integer, and it just doesn't work reliably. Even today, on the Mac OS and on the Linux system, the size of an unsigned long varies between those machines, and why? What purpose does that solve? It's just, you should have fixed sizes for things, and the more modern languages are doing that. One of the early decisions I made was Unicode all the way, which turned out to be right. EBCDIC is dead, Radix 50 is dead. Code pages are dead, or the character code pages are dead. Just forget about all those technologies. Where I goofed up was I also supported UTF-16 and UTF-32, and experience has shown that those don't work. It's too clumsy to support all three. Just standardize on UTF-8. Yes, I know that Windows uses UTF-16. And the way to deal with that is to, when you're getting input for your program, you convert the UTF-16 to UTF-8, you do all your processing, and when you write it back out to Windows API, you convert it to UTF-16, and that really works great because now you have only one set of string processing functions. They're all UTF-8, they're all standardized, and all you worry about is input and output translation. However, you can take that too far. We experimented, well, we didn't experiment it, we just simply did it, of trying to hide the fact that it's UTF-8 and multiple code units make up a character with a technique called auto-decoding. And auto-decoding was a complete disaster. The thing is, it's a great idea, and people were really in favor of it, and they had really good arguments, but the problem is, surprisingly, it turns out very few string algorithms actually need to can actually work on UTF code units without ever bothering to convert them to code points. So that if you're converting them to code points and hiding the fact that it's UTF-8, it starts making your algorithms very slow. And when your algorithm is slower, what happens to your users? They're spending all their time trying to defeat the auto-decoding instead of actually getting any actual work done. So there's a lesson there to try not to make your language too high level and trying to hide away what's happening underneath, because your users will always try to punch through that in order to make their program or their code perform. Too many choices. Well, there's a siren song there. The most famous example is probably C++ in the 1990s, which didn't come with a string class. And so guess what happened? Everybody invented their own string class. None of them could talk to each other. It was a giant zoo and a giant mess and just nothing but trouble. Even a bad string class is better than no string class, or I guess not bad maybe isn't the right word, but one with limited abilities. One thing that influenced me was I talked to a manager at Microsoft who said everybody marked out their debug code with their own invention. And of course, the problem comes in is when two teams have to start working together, their conventions on how debug code is inserted were completely incompatible. So, as I've said before, you wind up with a big fight about which side wins. And the way you circumvent that is you just build it into the language. Now, I know it just seems weird to build in debug support or debug code insertion into the language, but believe me, it's very effective, and you don't have arguments from people about it. Another neat thing that happens when you build it into the language is you can assign special semantics to it. For example, what did debug code often do? It often prints something, calling printf or write line or whatever. But pure functions don't allow you to do I/O from them like that. So then it becomes very difficult to debug your pure functions. So what the special semantics we assign to the debug code sections is it says, he knows what he's doing, let him go ahead and violate purity in the debug section. Makes it a lot easier to add debug stuff to your code. A similar example is the assert. Assert tests for things that test the state of your program to verify that it's not something unexpected. This is often done with macros. But the problem with that is then, of course, people develop their own asserts. And we run into the same darn problem with it. So the right approach is you just build it into the language, and building it in makes it reliable, predictable, configurable. One neat thing you can do with it is its semantics still apply even when the assert is, the code generation for the assert is disabled. The semantics are still there, and presumably your optimizer can take advantage of that to optimize the code following the assert. Another thing you can do if it's built in is you can pretty print the expression that failed. And I kind of thought that, yeah, who needs to pretty print the expression that failed? Because when assert fails, it gives you the file and line number of where it screwed up or where the failure was detected, and the user can just bring that up in their editor and it's no problem. So other people added this into D because it's a community project, and it turned out to be very popular to have the assert pretty print the expression that failed. So even I can often be wrong about these things. Some languages suffer from pointless, useless flexibility. And my favorite whipping boy, C, is has this with the suffix on an integer literal to say whether it's a long or not. It allows both lowercase l and uppercase l. Why do both need to be supported? That you wind up with coding standards like the Joint Strike Force Fighter standards, which says you shall not use lowercase l as an integer suffix because it can be confused with another numeral 1. In fact, that just happened to me at this conference because the WhatsApp link in it had a lowercase l in it, and I mistook that for the digit 1, and I kept typing it in, and WhatsApp kept saying, I can't connect you to the chat. And I finally realized, oh, I wonder if that's an L. And I changed it to an L, and then it worked. So anyhow, do you really want a coding standard document that says thou shalt not use lowercase l? No. You want to save everybody some time and just pick one in your language, and you're done. User extensibility. One big thing you'll want your users to be able to do is invent their own math types. For example, you might want to support a longer integer type than is supported by the compiler, or the user might want to. Or he might want to have an integer type with different kinds of arithmetic, like saturation arithmetic instead of wraparound. And a good test of your language is how close can a user get to defining their own integer type or their own floating point type. Or, yeah, because some of the gamers like using half floats, which are 16-bit floating point values. And the fun thing about half floats is there are so many different types of them. All fit in 16 bits, and different people want to use different ones. And do you really want to wire all those things in your compiler? you're not going to want to do that. So in order to make that work, you're going to need to support operator overloading, literals for your custom type, and deal with implicit conversions. All those features you're going to need. It really relieves pressure on the language. And I found that out the hard way, of course. I always do things the hard way. I thought it would be great to build complex numbers into the language. And it turns out that getting it right when you have mixing the real numbers and the imaginary numbers and getting all the combinatorics right at every stage of the optimization process turns out to be surprisingly difficult to do. So one of the best things we did was we took complex numbers support out of the compiler and put it in the standard library, and everybody was happy, and we got the semantics right on it. So the problems just went away when we did that. Here's an important one, is you really make your language easier to learn and easier to use if things that look like they should work, work. So here are some examples. And again, C and C++ users will recognize these as nested functions. Why can't I just declare a function inside another function? I know some people, they learned with C and grew up with it. Sometimes it never really occurs to them that they can't do this, or that it should be possible to do this because C didn't support it. But nested functions are a really nice feature, and it's just a simple example of why do my functions always have to be at the global level. The next one is, you'll notice in the grammar on language a thing called a constant expression. And a constant expression is a subset of the possible expressions that can be evaluated at compile time, and they almost never include functions. Why can't you execute a function at compile time to initialize a const value? It's just the most peculiar limitation. Fortunately, most modern languages these days are opening the door towards executing functions at compile time, and it's really kind of transformative on their code, surprisingly transformative. All the things you can do when you can start running your functions at compile time. Another thing that looks like it should work but doesn't, and just seems kind of dumb that it doesn't work, is why can't you do forward references? Why do you have to declare things before you use them? Well, it's an arbitrary random limitation, and if you can avoid having that problem, you will have a nicer language. One thing I learned early on was, in the old days, memory was extremely limited for the compiler, so most languages had a maximum number of characters you could have in a string literal. And if you exceeded that, then you had to create a nice error message for the user and print it to the screen. And why even have such a limitation? The only limitation should be you run out of memory. So it turns out to actually be less code to implement. Put as many characters in the string literal as you want up until all the memory available, and it will work. And this makes the language simpler. It means that there's less that you have to document. It's easier to learn. It's, anytime you have a limitation like 57 characters in a string literal, whatever, it looks arbitrary. It is arbitrary. Every time you have arbitrary constraints like that, you can do better. One thing I like is casts are dangerous operations. because a cast bypasses the type system and forces a type conversion. So if you're doing a code review, how are you gonna, you would want to pay special attention to casts because of the risk. The problem is you can't find them in code because they're a special form of the syntax with parentheses, and it's really hard to, grep for parentheses of things because parentheses are used all over the place. So the idea is for your more dangerous constructs is to make them easily findable, and this was a suggestion from Matthew Wilson to do this, and it turned out to be a great suggestion. You make cast a keyword and you put it in front, and it also has the lovely effect of you don't need a symbol table. Because it turns out in C that nearly all the problems with the non-context-free grammar is determining the difference between a type and a non-type, and that determines what the meaning of a parenthesized expression is. But by putting that keyword in front, remember I said it was easy to fix, it just that they couldn't fix it? This is the fix for it. All those problems just go away. By the way, I like P51, so. Interesting thing is the redundancy in the syntax. Famously, here over and over again, the compiler spits out an error that says missing semicolon at the end of the line, and the user's perennial question is, well, if the compiler knows it's missing, why doesn't it just put it in? And that's a very good question. And the reason is because it enables the parser to detect errors. Because if there was no redundancy in the language, any random string of gibberish will be a valid program and will be the compiler will be completely unable to help you debug it. Also, if you do have an error in your program, this extra syntax sort of is a way to get the compiler back on track so it can continue parsing your program looking for more errors instead of just quitting on the first error. Every once in a while you'll see a language that thinks that this is all wrong and semicolon should be implicit, like JavaScript, anyone? And JavaScript really went to great efforts to make implicit insertion of semicolons work, and it just does not work. Okay, English is kind of the same way. I hope that sentence up there explains why we have semicolons. If you read it carefully, you know where the periods go, but it's really hard to read because there are no periods in it. Has anybody seen those ancient Greek texts that just a block of text with no punctuation? And I find them completely undecipherable. Punctuation is a great thing, and semicolons are needed. Making code easier to read, also just simple things like being able to use an underscore to break up numeric literals to make them instantly recognizable as, let's say, a phone number as opposed to just a random bunch of digits. And I stole that idea from Ada. Ada is a great language, by the way, very innovative. Now you notice that some of the things I say are actually contradictory. And so I talk about regular syntax and all this stuff, but sometimes you want the syntax to be irregular. And because making it irregular helps find bugs. Has anybody written a loop like this? Yeah? Did you find how long did it take you to find the error in the loop? Yeah, I remember one guy who was a very good programmer, and he finally comes to me telling me there's a bug in the compiler. Because he spent 2 or 3 days and there's nothing wrong with his loop and it only executes one time. And I looked at it and said, you got a semicolon there, or an extra semicolon. And he goes, oh my God, I spent 2 days or whatever trying to find this bug, and it was just an extra semicolon, because you get used to writing statements and you hit the semicolon key. So at that point I decided that to add an irregularity to the syntax where you simply can't put a semicolon there, even though you can in C. In fact, since that time, C and C++ compilers will actually warn you if you do that, because it's such a common error and so hard to spot. Here's another helpful irregularity, is if I have nested declarations of the same variable it's called shadowing, because the inner one is shadowing the outer one. And especially if you have a lot of code, so there's a lot of separation between those lines, this becomes an error in your program that is nearly impossible to spot. So having the compiler come to the rescue really helps a lot. It just simply says you can't do that. You can't have shadowing declarations. Another improvement you can make to your compiler is lowering, which was defining some syntax sugar in terms of other syntax. For example, a while loop can be transformed into a for loop, and the advantage there is all you have to do is rewrite the while loops and the for loops, and you can forget about doing any further semantic processing or code generating for the while loops, as long as your transformation is correct. And it is pretty easy to do. You know that if the for loops are right, your while loops are right too, so it saves you a lot of time. Good language is composable with smallish building blocks, orthogonal. The fewer special cases and edge corner cases are better, so the user can combine them. It's sort of like Legos. You want your compiler's basic things to be like Legos. It reduces the size of the language and increases the things that your users can build with the language. Math, of course, is the king of composability. Everything works, is composable. APL, a very old language, is very composable and shows how far you can go with it, because there almost every string of characters is actually a program. D is not so composable. For example, you can't insert a statement inside of an expression. Okay, some examples of composability coming up. Expressions, I already mentioned those. The next two I'll get to. Universal function call syntax. Started out like the expression at the top, and it turns out that is very hard to read. It's very hard to see where the flow of control works. What universal function call syntax is you can take the first parameter out in the parameter list and stick it in front of the function and then have a dot, so it kind of looks like a member function. And the rewrite on the bottom, and this is done by lowering, it lowers the bottom one into the top one. It's very easy to see what's happening. Your program and your data and just has a natural flow from left to right. And since we all read from left to right and are very used to it, and yes, I know there are some languages that read right to left, but most of us read left to right. And by doing it this way, the expression becomes much more natural to read and understand. And this can go further. In C++, this would be called iterators and algorithms. In D, it's called ranges and algorithms. And you can see how I can write a whole program this way. I can read from stdin, copy, take them by lines, turn them into an array, sort the array, and copy the result to an output. And this is a very nice way to program. And you have all these building blocks with your ranges and algorithms where you can hopefully snap them together in any order, like in a vector set. One of the problems you can get into with operator overloading is things like this happen. And what's wrong with this? It doesn't flow from left to right. The O stream appears to flow from right to left, except that it depends on whether it's the beginning and the order of evaluation of the operands. And the I stream, you know, your stream does not flow that way. So generally, trying to support being able to redefine operators like this is a bad idea, even though you need to support operator overloading to create your own arithmetic types. So I've tried to block people from doing things like this. And here's a more serious example, which turns, with expression templates, it turns C++ into a regex language, a DSL. And I'm going to get myself into trouble by saying this is a very bad idea because it looks like C++, but it's not. It's a domain-specific language. And these kind of things, if you can find a way in your language to discourage these kinds of things, is for the better. And this is one of those things you only find out. It's one of those great ideas. I mean, everybody loved expression templates when they were kind of discovered in C++, but it just leads to bad programs. One thing that's happened, and it's really easy to see the end product, but when you reach the end, in the beginning you don't see it. And here's the evolution of lambdas in D. It starts out with something that looks like a regular function declaration, and it gets shorter and shorter and shorter and shorter. Each time we find ways to boil down and remove more of the syntax, and it becomes, much more pleasing. Similarly, loops started out like this, and they evolved into structured programming with a specialized loop construct. And then that went further by turning it into a for each, which did the iterations for you, which then turned into ranges and algorithms form. And now finally we get to the best programming idea that does not work. Anybody have an idea what that is? No? No? This is my most controversial one, so I saved it for last. Macros. Macros are the most pernicious, dangerous, bad ideas that keeps creeping back into programming languages. And to illustrate, I have a story. I had a friend who worked at Microsoft, and he was talking with a manager who had a 50K binary program that had been written entirely in assembly language that had a bug in it. And he'd given that program to programmer after programmer at Microsoft, and none of them could fix the bug because they didn't understand it. Because the guy invented his own, or he'd used the macro programming abilities of the Microsoft assembler to invent his own language. And his own language was naturally completely undocumented. Nobody understood what it did, and so nobody could fix the program. So my friend said, oh, I can fix it. So he gets it, and he takes the source code, and he has it fixed in 2 hours, and he checks it in. So the manager was astonished and said, how did you fix that in 2 hours? How did you figure out this guy's domain-specific languages? And he says, I didn't. He said, and this is the reason why he told me the story, is I ran it through Walter's disassembler, which produces assemblable assembly language. And then the bug was obvious, and I fixed it, and I checked in the disassembled, reconverted to source code as the new version of that program. So this is when the light bulb went into my mind that there's something wrong with macros. because I see this happening time and time again. And I used to be a big fan of macros. So the first programming language I designed was, ABEL, and it had macros. And then I started noticing this problem cropping up elsewhere. It apparently happens in Scala. I have a sneaky suspicion that the reason Lisp has never become a mainstream language because in order to use it, you have to use the macro system in it. And so everybody creates their own version of Lisp, which is incompatible with anybody else's. And so the language as a force never particularly gelled. The problems, as usual, it's always undocumented. The debuggers don't understand it. It makes building an integrated development environment unreasonably difficult. Your poor successor is going to hate you and hate your DSL because he doesn't understand it. And it balkanizes the language into multiple different languages, all incompatible with each other. So, in conclusion, more power isn't always better. Sometimes constraining options leads to clarity and consistency. Composability and orthogonality are a big deal. The idea is to eliminate tedious machinery with syntactic sugar and build in things that are very commonly used. It's worth building into the language to make it convenient. So questions? Oh, so man with the microphone.
I'm curious about the decision between having unlimited string length versus having null terminated. Because I presume if you don't have unlimited string length, you have to set some character which would be a limiter, which is usually null character. Was there any problem with that, or is it already set in stone that we want to have it like this?
Whenever I review C code, the first thing I look at is their use of the string functions. And I can tell you that 90% of the time I find a bug in it. And it's always a bug because of that null character. People are always getting off by one errors in their string processing. Because do I include the null terminator or do I not include the null terminator? And sometimes it's very difficult to see what happened with it. The other problem with the null termination is you find yourself constantly scanning to find the null to find out how long it is. So null terminated strings are really useful only when you have an extremely memory constrained system. If you do not, it's a bad idea. And you should have length delimited strings, not sentinel delimited strings.
Thank you. Thank you.
More questions? Come on, I expected controversy. It's fun arguing about this stuff. You can't all agree with me. I know, I bet you like macros, right? You're smiling over there. No, you're shaking your head no? No, not me. How many use macros in your code? Come on, be brave. I won't take any names. Well, I guess that's it then, and I'll be around nearby for the next hour or so if you want to come and argue with me. It'll always be fun. Oh, we do have another question.
Maybe a question from me. What do you think about this concept of ranges in C++20 or in Boost? Is it better than several loops over some collection, or do you prefer to construct these with the ranges, with this pipe operator and so on? I'm not sure if you are familiar with.
So is your question about using a pipe operator versus using the dot operator?
No. My question is about constructing function in C++ with the several for loops to, for example, to filter some element from the collection versus doing this with the these ranges filtered that was added in C++ 20.
So are you asking iterators versus ranges?
Yeah.
The trouble with iterators are a generalization of pointers, and ranges are a generalization of arrays. And the difference is that a pointer has no notion of where it's supposed to end, and a range, being based on an array, does. So a range is self-contained, whereas with iterators, you have to wind up with iterator pairs to make it work. So personally, I think ranges are a superior mechanism to using iterator pairs. I think it's memory safe too, because there isn't an arbitrary association of two pointers. It's a pointer to the beginning and a length as a pair. So we have that in D, and it's worked with much more successful than I'd hoped it would. But I don't. C++ has their own notion of using ranges, and well, that's up to them. Eric Niebler is a good friend of mine, and he argues for the iterator pair approach. And so we've argued about that many times with no resolution. So my opinion isn't the only one on that. So more questions? All right. Well, I'll be around for anyone who wants to ask me more questions. So thank you very much.